So welcome back to the problem solving session. So I'll just share my screen and we'll start. Okay, so I hope that the screen is visible to you as well as I am audible to you, right? So this is week 7 for the ecology and environment problem solving session, right? So till week 6 or in the week 6 session, we discussed about wastewater treatment, different stages of wastewater treatment, and we studied some concepts related to food to microorganism ratio, right? So today we'll continue on to that path and we'll try to solve some numericals and understand the concepts a little bit more clearly. Okay. So as per the sessions or last week or the from fifth, sixth or seventh, fifth and sixth week session, we understood how water is getting polluted, what are the different contaminants, and why treatment is necessary, right? So when we talk about wastewater treatment, uh, just to provide you a recap, so it is basically any method which is removing the contaminants from wastewater so as to get a treated water which is safe for reuse or safe for discharge into the environment, right? Then we studied the different characteristics of wastewater, what are the physical and chemical constituents, inorganic and organic chemicals, gases, and the biological constituents also. Okay. Now moving towards the wastewater treatment stages, we studied there are three main treatment stages: primary, secondary, and tertiary. So primary or the preliminary is basically aimed at removal of large materials or floating debris. In secondary, most of the degradation of organic matter takes place. Your BOD gets reduced. Then in the tertiary, you have basically ultraviolet disinfection or ozone treatment where the biological contaminants or the pathogens are removed from the secondary treated water. Okay. Now, then we discussed a little bit about different technologies that are available for preliminary and primary, tertiary and disinfection. Most or more or less the technologies are common, but we have quite a lot of variety for secondary treatment. So then coming towards the hydraulic retention time. So we studied about the hydraulic retention time or the HRT. So let me just okay, so we see that there are very few participants today. Fine. Okay. So when we talk about hydraulic retention time, so it is basically the length of time a particle or unit volume of wastewater remains in the reactor. So this HRT is very important because if suppose waste material which is to be treated, if that remains for a very short time in the treatment unit, then the treatment will not take place accurately, right? Also, the same may happen if it is uh, staying in the treatment unit for a very long time. So, providing an optimum HRT is very crucial, right? So, if you want to understand HRT, it is basically you have to suppose you fill a tank with wastewater. Okay, so HRT will be the time that a drop of water will remain in the tank before the tank is completely filled and the drop of water flows out, right? So suppose you have a treatment unit, so what will be the HRT? HRT will be the time for which this droplet stays here until and unless the entire tank is filled and the droplet flows out of the tank. So this is important because it has to stay in the for the appropriate amount of time in the reactor so that the microorganisms can act on it and the organic matter can be degraded. So normally the HRT is 4 to 8 hours when we talk about activated sludge processes or secondary treatments. So mostly it is 4 to 8 hours. And the formula is volume by flow rate. So HRT is V by Q. V is the volume of the reactor and Q is the flow rate. So flow rate for the wastewater which is flowing in that particular tank. So that is here gives your HRT. Now we studied one example. So here we are having two different examples, right? So first is that you have a treatment unit. Okay. The dimensions are provided. So it is 1.5 meter wide, then it is 20 meter long, and it is 2 meter deep. Fine. So we discussed this in the next previous session as well. And the flow rate is 0.5 meter cube per second. So what will be the hydraulic retention time? So you have to calculate the HRT and your flow rate is provided 0.5 meter cube per second. Correct? So what will be the hydraulic retention time for the treatment unit which is having following dimensions and the flow rate of the wastewater is this. So I'll suggest you try to attempt this and solve it. We have already done it, but just a recap because last time we could not discuss it in detail. So just try to solve this. All the dimensions are provided and the flow rate is also provided. What will be the HRT? And HRT is a V by Q, right? That is flow rate by, volume by flow rate of the reactor here. So HRT is volume by flow rate. You have to calculate volume, all the dimensions are given and the flow rate is also given. So I would suggest you try it. The participants which have joined the lecture, please try the question and provide the answer here in the chat box. I can see some people are joining. Okay, see this is the question, example 1. So try to attempt it. You have to calculate the hydraulic retention time. All the dimensions and flow rate is provided and time is volume divided by the flow rate, right? So try to solve this. It is a very simple, straightforward numerical. Then we'll go on to the next question. Okay, let's see if any one of you is okay. So the flow rate is given to us as 0.5 meter cube per second, right? And the volume was also given as one volume you can calculate by multiplying the length, breadth, and the depth. So it will give you 60 meter cube. You just divide the volume, which is 60 meter cube, by the flow rate, that is 30 meter cube per minute, and you will get the HRT as 2 minutes. So your hydraulic retention time for this will be 2 minutes. What you have done? Just simply multiplied the dimensions to obtain the volume, divided it by flow rate, which you have, the flow rate you have converted it from meter cube per second to meter cube per minute, and the hydraulic retention time is 2 minutes for this particular unit with a flow rate of 0.5 meter cube per second, right? Now the next question is similar. This is also quite similar. So flow to a rectangular basin is 3 million gallons per day. The basin is 100 feet in length, 50 feet wide, and 15 feet deep. Calculate the aeration basin's hydraulic retention time. So this you should solve now because already this solution is provided to you, right? So similarly you have to do this. You just have to take care of some of the unit conversions. All the dimensions are provided: 100 feet length, 50 feet breadth, and 15 feet depth. And the flow rate is 3 million gallons per day. So what will be the hydraulic retention time? Try to attempt this. Calculate the HRT by using the clarifier volume and the flow rate. So let me see if anybody of you is attempting to solve this. Fine. So what you were supposed to do in this question is, first you will calculate the volume. How will you calculate the volume? Volume will be 100 multiplied by your bread, that is 50, and then you have to multiply it by the depth, which will be 15. Fine. So this will give you the volume in feet cube. After obtaining the volume, you have to convert, first see about the flow rate. So flow rate is 3 million gallons per day. Fine. So what is this? This is 3 into 10 to the power 6 gallons per day. Right? So now what next has to be done is you have to divide the volume by flow rate. So hydraulic retention time will be, suppose this entire value comes out to be x, right? So this will be x feet cube divided by 3 into 10 to the power 6, because it was million, so 10 to the power 6 will come, gallons per day, right? Now what you have to do is you have to apply a unit conversion where 1 gallon is equal to 0.133 feet cube. Okay, so you had to simply apply this unit conversion here, right? So when you will apply this gallon will be replaced by 0.133 feet cube. Fine. So this feet cube and this will be cancelled, right? So you'll get the answer in days. So you will get the hydraulic retention time. Simply what you had to do was multiply the length, breadth and depth to get the volume in feet cube, then divide it by flow rate, which was in gallons per day. So for that you converted gallons into feet cubes. So feet cube and feet cube will be cancelled. You will get the answer in form of HRT. So finally you will get hydraulic retention time in terms of days. Correct? So I hope these two numericals clarify your doubts regarding any doubts regarding your obtaining the HRT when the reactor volume as well as the flow rates are provided. Then the next concept which we studied was food to microorganism ratio. Now so as the name suggests, food to microorganism ratio is available food divided by the microorganisms which are present in the reactor. So we have already discussed that the role of microorganism is degradation of organic matter and thereby reducing the BOD. So available food will be the organic matter. So in other terms what you can say is available food is BOD, and we discussed that microorganisms are indicated by MLVSS. Right? So this was already briefly discussed in the last session. So available food is the organic matter which is present. Microorganisms are the biomass which are there in the reactor. So basically F by M means organic loading per unit weight of microbial mass. So this can also be written as food is BOD or COD in kg per day. So as I told you, food will be BOD in kg per day. So remember you have to input this in terms of kg per day. And microorganisms are MLVSS. So this will be in your kg. So F by M ratio will be kg per day of BOD per kg MLVSS. Right? And most treatment plants, they operate at an F by M ratio of 0.2 to 0.5. So this is the F by M ratio which is usually maintained in the treatment plants. Now usually sometimes in the numericals you are not provided with directly with the MLVSS value, which is mixed liquor volatile suspended solid. So this is just a measure to denote the microbial mass which is present. So you may be provided with MLSS. So you have to remember that MLVSS is 80% of MLSS, right? So again, this is very straightforward equation. You have to just divide BOD or COD in kg per day with the microbial mass which is present in the reactor. So that will give you the F by M ratio. Correct? Now we have an example. So if wastewater with a BOD of 200 mg per liter is treated in a tank with 6 hours HRT and having 4000 mg per liter MLVSS, then F by M ratio will be what? Right? So I don't think any of you will provide any answer. I'll just see if... So you can try and attempt this. We have already discussed it. So if first initially if you do this, then we'll go to a next numerical, right? See, the BOD is given as 200 mg per liter. HRT is provided 6 hours and MLVSS is 4000 mg per liter. So available food was your BOD or COD in kg per day, right? So for this, you will calculate BOD or COD in kg per day, correct? So 200 mg per liter and BOD is 200 mg per liter, fine. So you will have to divide it with your 6 hours. You convert it into days as well. So that will give you in kg per day. After this, you have to divide it by your microbial mass, which is 4000 mg per liter. So if you divide it directly, these values will get cancelled and you convert this into days, so you will get it as 0.2 day inverse. Now after this, there is another example. You have raw sewage with BOD of 220 mg per liter applied to a conventional sewage treatment plant based on activated sludge process. Okay, so there is a sewage treatment plant and it is based on the activated sludge process. The BOD of raw sewage is 220 mg per liter. After this, if the primary treatment removes 25% of BOD, so this is activated sludge is obviously your secondary treatment process, right? Now between this, you have a primary treatment process. Fine. Now what does it states? Primary treatment removes 25%. So this removal of 25% is achieved by the primary treatment. Determine the MLVSS to be maintained in the reactor to control an F by M ratio of 0.6. Now if you want to have an F by M ratio of 0.6, what will be the MLVSS that should be maintained? Okay. Flow rate is provided 0.5 mld. So this is your Q value which is provided, right? So what does the question states is, there is a treatment plant with 2 units. One is the primary, other is a secondary. In secondary, you have an activated sludge process, right? First data provided is that the BOD of raw sewage is 220 mg per liter. Now the F by M which should be maintained in the reactor is 0.6. So what will be the MLVSS that has to be maintained? And the flow rate is given to you as 0.5 ml. So we know that F by M is BOD or COD in kg per day, right? So you have to first calculate BOD in kg per day divided by MLVSS in kg. So what is there? You have this value. This is 0.6. This is to be calculated, let's say X. So you have to first calculate BOD in kg per day, right? So how will you calculate BOD kg per day? First what you have to do is, it is saying that 25% of BOD is removed. So that means what is left is 75%, right? So the BOD first remaining in secondary will be 75% of 220. So that will give you the actual BOD value. After getting the actual BOD value, you multiply it by flow rate, that will give you BOD in kg per day. Okay. So let's see how it's actually done. So influent BOD is 0.75 into 220 mg per liter. Why is this so? Because we are talking here about the secondary unit process. That was your activated sludge process, right? In the secondary treatment, 75% BOD is left because 25% is already removed in the primary treatment. 25% has been removed in primary, so 75 is left. So that is why you multiply 0.75 into 220, you get 165 mg per liter. This 220 is the BOD of raw sewage. Fine. So this will give you the first of all the influent BOD. After this is in mg per liter. You have to convert it into kg per day. So what has to be done? You have to multiply it by the flow rate. Flow rate has already been provided to you as 0.5 mld. 0.5 mld means 0.5 million liters per day. So for million you will put 10 to the power 6 liter per day. So this is your flow rate. So when we apply the flow rate here, if 0.5 to 10 to the power 6 liter per day, this will get cancelled. You will get 82.5 kg per day as the BOD per day. Okay, so this 82.5 kg per day, this is the food which is available to the microbes. So this is your F value. Fine. Now what we have to do is F by M is BOD per day by MLVSS. You have to calculate MLVSS, just simple cross multiplication. So we will get 82.5 by 0.6, that is 137.5 kg. So this 137.5 kg microbial biomass is to be maintained in the reactor to have an F by M ratio of 0.6, provided the food available is 82.5 kg per day. Okay. So this is your final answer, 137.5 kg MLBSS is to be maintained. This was asked that determine the MLBSS to be maintained, right? So what you had to simply do was, first you have to see that the BOD which is provided is the BOD of raw sewage, and the BOD which is remaining in the secondary reactor is only 75%. So you simply calculate the actual BOD available in secondary reactor, right? Then second step is you multiply it by the flow rate to get the BOD value in kg per day. Then you have to just simply put it in the formula, apply cross multiplication, and you will get the MLVSS, right? Now suppose the volume of, if you are provided with a volume that is 57 meter cube, okay, so suppose the volume of the reactor is 57 meter cube, then there is another relation which helps you identify the concentration of the biomass. So the biomass concentration is flow rate into the substrate available divided by the volume, right? So what you do is you have the MLBSS value, that is 137.5 kg. Then you convert, this is just for unit conversion, right? And you apply the S naught value dividing by the volume of the reactor, which is 57 meter cube, right? So what you have to do is just simple divide the Q into S naught, that is your F by this microbial biomass, by the volume. You will get the biomass concentration. Obviously, what do we mean by concentration? Concentration means amount, that is your in mg or in kg, divided by the volume, right? So you have the amount, that is 137.5. You just simply divide it by volume and apply some of the unit conversions to get the answer in mg per liter, right? So this is just to show how the calculations are done when we have the BOD values as well as the FYM ratios or the MLBSS values. Fine. So I hope this example is clear to you. You just had to convert the BOD into BOD kg per day and then simply obtain the microbial biomass. Now when we talk about the wastewater treatment, there are different types of reactors that can be employed. So there are batch reactors, complete mix reactors. You have such reactors, complete mix reactors in series, or a PFR, that is plug flow reactors, packed bed. So there are very different kinds of varieties of reactors that can be employed for wastewater treatment. Usually the main difference is between a batch reactor and a continuous reactor. What happens in a batch reactor is you put in wastewater, let it allow to be treated for say X hours, and then you just withdraw the treated water. That is a batch reactor. Nothing is added in between and nothing is removed. Fine. But what happens in a continuous reactor? There is a continuous inflow and a continuous outflow. Okay, so your system is in continuity. There is you don't have to wait for certain period of time to obtain the to withdraw the effluent. So that is a basic difference between a batch and a continuous reactor. Now we'll study CSTR, or the completely mixed reactors. So completely mixed reactors or completely stirred tank reactors, these are very common CSTRs. So in this, it is assumed that mixing is taking place continuously and uniformly throughout the reactor. So let's say this is a CSTR. Inflow rate is Q and the concentration of a particle is C naught. And in the outflow, you have the concentration is C and the outflow is represented by Q. So you see that the inflow and the outflow rates are the same. Now this is a schematic diagram of CFSTR, that is a continuous flow stirred tank reactor. V is the reactor volume. Q naught is the flow of the influent, that is the wastewater which is going inside, and the inflow will be equivalent to the outflow. So both are represented by Q naught. C naught is the initial concentration of any component or reactant in the inflow, and Ce is the outflow concentration. Right? So this is just a simple representation of a continuous flow stir tank reactor. Now these are some of the relationships for relations that are developed for the CFSTR. Fine. So when we talk about CFSTR, concentration of these will be helpful when you go for solving some numericals that are based upon this reactor dynamics, right? So Ce, that is a concentration in outflow by inflow, is represented by this. So where K is the reaction time constant, reaction rate constant, and T is the reaction time, or it can be also the called as HRT. Fine. So when you take this convert this hydraulic retention time, so we know hydraulic retention time is volume by flow rate, right? So you replace this by volume by flow rate, what you will get is Ce by C naught is 1 by 1 plus K into V. So you replaced the hydraulic retention time by this, that is volume of CFSTR divided by the flow rate of the wastewater. So when you solve this, you will get that volume is equal to flow rate by the reaction rate constant and C naught by Ce minus 1. So this is the initial concentration. This is the final concentration or concentration in the effluent, right? So C naught and Ce will vary. K is a rate constant and Q is your flow rate. So this relation can be used to identify to determine the volume of a CFSTR. What volume will be required if you have these kind of input parameters. Okay. So we'll try to solve a numerical based on this. If there are any doubts till now, you can ask me, post it in the chat box or unmute yourself. Otherwise, we'll solve these numericals and after this, we'll go to the Q&A session, right? So, are there any doubts regarding the concept of hydraulic retention time or the food to microorganism ratio? So, we have covered three main concepts, that is your hydraulic retention time, FM ratio, food to microorganism ratio, and the now we are going to do a numerical on the reactor volume, where we are studying with respect to CFSTR, that is a continuous stir tank reactor or a continuous flow stir tank reactor. So let me just check if there are any doubts. Okay, so why is there disturbance? So is it only on your side or others as well? Is everybody facing this problem? Is there some disturbance regarding the audio or the video? Okay, it's clear, fine. So I see that nobody is replying, nobody is having any doubt. So we can continue then. Fine. So what has been provided is, you have a component or a reactant, let's say A. Okay. In 1.2 mld flow, if the concentration of reactant A in 1.2 mld flow of wastewater passing through a CFSTR is reduced from 250 mg per liter to 15 mg per liter, determine the volume of the reactor. Assume that the reaction rate is of first order, having a rate constant of 0.5 day inverse. Right. So I'll just give you a minute to read the question carefully. And if you understand it, you can also go through the answer and we'll also discuss the solution. So I've already provided you with the solution, right? Just to clarify your understanding for this concept. So read the question carefully, what all is provided to you and how the solution is being, how you are approaching towards solving the problem. Fine. So what is provided to you is, you have the concentration of reactant in the inflow and the outflow. So what you have to do is, you have to determine the reactor volume. So obviously we'll be using this relation to determine the volume of reactor, where this is the inflow concentration, this is the outflow concentration, Q is the flow of the wastewater, and K is the reaction rate constant. C naught and C are your reactant concentrations. You use this to calculate the volume, right? So this is the relation. It is written here as well. Fine. So first thing which needs to be identified is your Q. Q is the flow rate. So Q is provided to you as 1.2 mld. So first what you have to do is, everything is provided in mg per liter. This is also in mg per liter. This is J inverse, right? First what you should do is convert this into meter cube per day. Fine. So what will be done is 1.2 into 10 to the power 6 liter per day, because this is million. So you replace it by 10 to the power 6. After this, you convert liter into meter cube. So what will happen is 1.2 into 10 to the power 6 by 10 to the power 3 meter cube per day. So this will give you 1.2 into 10 to the power 3 meter cube per day. So this is the flow rate. Okay, so Q is provided. We have Q, that is 1.2 into 10 to the power 3, or this will be 1200, 1200. Fine, yeah, it's 1200, right? Then 1 by K. So K is already provided, 0.5 day inverse. You just simply put 0.5 day inverse. C naught by CE. So C naught is the initial concentration. So initial is 250 mg per liter. So you have 250 mg per liter by CE, which is final 15 mg per liter. So 250 mg per liter by 15 mg per liter minus 1. So you see this will automatically get cancelled. Fine. So what you will have is V is equal to 1200 meter cube per day, because this 1200 goes into the numerator part. You just have to simply apply cross multiplication. So V will be 1200 meter cube per day by 0.5 day inverse, and you have 16.66 minus 1. So again this will get cancelled. You will get the volume in terms of meter cube. So volume is approximately 37,600 meter cube. Correct? So again this was quite straightforward. What you had to do is just apply a unit conversion to convert this million liter per day into meter cube per day. Right? Because ultimately the rest of the units will get cancelled and you will left with only this unit. So if it's in liters, it will create a confusion. So because you can get the volume in terms of meter cube or liter anyway, right? So in this question, we were provided with the CFSTR. The initial concentration was provided as 250. Final concentration was provided as 15. You had a flow rate of 1.2 mld, and the K was provided as 0.5 T inverse. And we had to calculate the volume. So what we simply did was we used this relation, applied Q that was 1.2 mld, then K was 0.5 Day inverse. These values were provided. We simply solved it and we got the volume as 37,600 meter cube. Alright. So after this there is a short Q&A session. So today's lecture we studied three main topics that are related to your wastewater treatment. First is the hydraulic retention time. So where we studied that T, or the hydraulic retention time, that is volume of the reactor divided by the flow rate. Correct? So we solved two main numericals. So what you had to do was simply the dimensions of the units are provided. You multiply these dimensions to get the volume, and then you simply divide it by the flow rate, so you will get the hydraulic retention time. Similar thing was to be done in the second example. After hydraulic retention time, we studied F by M ratio, which is important so that the appropriate treatment takes place. Then simply we again did two numericals in this part. Your F by M ratio is basically BOD or COD in kg per day divided by MLVSS in kg, right? So we were provided with the BOD, HRT and MLVSS. Through these data, we obtained an F by M ratio of 0.2 Day inverse. Similarly, we solved another example where the BOD was provided as 220 mg per liter in the raw sewage, and we had to calculate the MLVSS that is to be maintained in the secondary reactor if F by M ratio is 0.6. Again, the flow rate is provided, and it is stated that primary treatment removes 25% of the BOD. So if 25% is removed, 75% is left. So we calculated the BOD in kg per day, and using this 0.6 we just simply calculated MLVSS. After calculating MLVSS, we just divided it by the volume and we got the concentration, right? Then there are different types of reactors. Today we studied CSTR, that is completely stir tank reactor. The relationship to this determine the volume of CFSTR, and followed by we solved a numerical regarding this CFSTR volume, right? Now the Q&A session is very simple. There are 4 to 5 questions. So screening and combinations or the combinators, these are preliminary treatment process. So these are based upon your basic idea or the basic concept of wastewater treatment. When we talk about screening and combinators, these will come under preliminary or not. So you have to identify whether this is true or false. I'll see if anybody of you is replying. So screening and communicators, fine, one student has answered, so that is correct. Because so the correct answer for this will be true, because this is a part of preliminary process whereby basically your coarse material or the large floating debris, not the debris but large floating material, is removed from wastewater. Why it is important? It is important because if there is very large material which is going into the treatment line through secondary or tertiary, it can damage the equipment or the machinery which is there, right? So that is why all the larger solids, they are removed in the preliminary treatment. So there are different screens through which it passes and it is removed. So we study, there is a diagram in the reactor part, yeah. So such kind of screens and communicators are there which basically remove your large solid material, right? So this will be true. Coming to the next question, dash devices remove materials which would damage equipment or interfere with the process. So this will be screening devices, obviously. Dash represents the heavier inert material in wastewater: debris, waste, screens, or grit. So what is the heavier inert material which is present in the wastewater, whether it is debris, waste, screens, or grit? Provide your option in the chat box. So we have already discussed this last week, where we discussed the different treatment stages. So you have to identify which of these is removed, and we discussed this during the preliminary treatment stage. So one of the student has answered B, waste. So waste is obviously not the heavier material which is present. The answer will be D, that is grit. So grit is your inert material which is present in wastewater, and it will not get decomposed during the treatment stage. That is why that means it is inert in nature. That is why it has to be removed during the preliminary or the primary stages. So we already discussed this, right? So grit is the matter. It is having a specific gravity of about 2.65, and the design is based upon the particle size. So there are different mesh sizes, where according to this mesh size, what will be the particle that will get removed from the wastewater. So grit is the inert material which is removed during the primary or the preliminary stage. What does zero discharge actually refer to? So when we talk about wastewater treatment, this is a very common terminology which is now used with respect to most of the industries. They claim that they are ZLD, which means zero liquid discharge. So what does zero discharge actually refer to? Zero discharge of ions. Reject is recycled from every part. Reject is not rejected out. Influent equals effluent or 100% efficient plant. So this is a very common term, that is your zero liquid discharge, right? So let me see if anybody of you has replied. Okay, so one has replied 10, that is your 100% efficient plant. So that will not be the answer. Anybody else? What will ZLD refer to? Whether it is complete recycle or zero discharge of ions, 100% efficient, or reject is not rejected out. Fine. So zero liquid discharge basically means, so it is not possible that if a treatment plant is actually working and there is no reject, so that is not possible. So this is completely wrong. 100% efficiency is not achievable. Zero discharge of ions, so this has nothing to do with the ion discharge. So your correct answer will be recycling. So zero discharge means that the plant is actually not discharging anything. It is completely recycling. Okay. So zero discharge refers to treatment plant in which reject is recycled. Okay. So you are just the effluent which you are obtaining, you're again using it as an infant and you're recycling it. So that basically refers to zero liquid discharge. Okay, so that was all for today's session, right? So if you have any doubts, just drop the message in the chat box so that we can discuss them. Okay, so if there are no doubts, you can leave the session and we'll again meet next week. Okay, so one student has doubt. Second question, fine. Okay, see, so the second question asked, what are your devices which remove materials which would damage equipment or interfere with the process? So the answer is screening devices. Why screening devices? Because see, the first and the second question are quite related. We already discussed in the first. So what is the thing is that you apply screens in the preliminary treatment and communitors. Why do you apply them? Because the large materials which are there floating in the sewage or in the wastewater, they can be removed. Otherwise, what will happen if they are not removed in the primary treatment? So when the wastewater will go in the secondary or in the tertiary stage, the machinery will be destroyed, right? So that is why screens are employed. Screening devices remove materials which would damage equipment or interfere with the process. So they have a varied application of treatment facilities. So see, when we see a typical conventional treatment plant, what happens is there are first screens. You see, these are the large particles which get attached to the screens. Then the particles which are even smaller than this, they get removed during the community through the commutators. After this, you have the grid chamber or the clarifier, and then this goes into the aeration tanks. Because if such large particles will come in the aeration tank, it will hamper the entire process and also it can hamper the machinery. Suppose you have very small aerators here, right? So such kind of particles, they will hamper these functions. So that is why large materials and floating debris, like you have clothes, pieces of clothes, or you have rags or sticks. See, it should be, yeah, you have rags, sticks, floatables. So these all are removed during the primary treatment or the preliminary treatment, and mainly through screens and communicators, right? So I hope this solves your question. That is why the answer here will be screening devices. And when we talk about inert matter is grit. So this is also removed during preliminary or primary treatment, but inert material is grit and the large floating materials are removed through screening. So first screening will take place. After that, after big materials are removed, after that the grit removal will take place. Okay. So I hope this solved your doubt. No, why so? What is the doubt again? What is exactly your doubt? You can either unmute yourself or ask or write it in the chat box elaborately. What exactly where you are confused? Okay, no doubts, fine. Okay, so if there are no more doubts, we can close this session and we'll meet next week, which will be the 8th session, right? Fine. So I'll just end the meeting.